All right, let's dive right into this comprehensive cockpit tour of the DHC-8 Series 400. Today, we're walking through the absolute core of the Bombardier Q400's flight controls. Whether you're a flight simmer, an aviation student, or honestly just an enthusiast wanting a deeper understanding of how these incredible machines operate, this explainer is built to give you a highly structured breakdown of the systems that keep this aircraft flying safely. Here's our flight plan for today's explainer. We're going to systematically break down the three primary axes of flight: yaw, roll, and pitch. After that, we'll move off the primary controls to hit the secondary flaps, the ground gust locks, and finally, the ultimate safety net, the stall protection system. Okay, so before we hit that first axis of flight, let's introduce a critical acronym we're going to see a lot today: PFCS, or Powered Flight Control Surfaces. On the Q400, your elevators, spoilers, and rudder require some serious hydraulic muscle to fight the intense aerodynamic forces at play. They just don't move by cables alone. Now, where does that hydraulic muscle actually come from? Well, it comes from the PCUs, or power control units. Whenever a pilot makes an input on the yoke or pedals, these hydraulic actuators installed inside the aircraft are the actual muscles doing the heavy lifting to move those massive flight control surfaces. And here's the really crucial point. This computer brain, the Flight Control Electronic Control Unit, or FCSECU, essentially acts as a safety limiter. See, as the Q400 speeds up, aerodynamic forces increase drastically. So to prevent structural damage, the FCSCU steps in and actively reduces the hydraulic pressure available to those PCUs based on the changing airspeeds. It's a brilliant piece of engineering. All right, let's get into Section 1. Primary Flight Controls, yaw. So yaw is commanded via the rudder pedals, right? And these are mechanically connected between the pilot and co-pilot via an interconnect rod. When you physically push the pedals, you activate two vertically stacked PCUs that power the fore rudder. But what's really unique here is that the Q400 has a divided rudder. Pushing that fore rudder mechanically pulls a trailing rudder section behind it. And that trailing rudder actually deflects twice as far as the fore rudder, giving the aircraft immense directional control. Moving right along to Section 2, roll controls and disconnect. You know, the roll spoilers aren't just for turning in the air. They're absolutely crucial on the ground, too. The aircraft automatically dumps lift and maximizes braking efficiency the exact moment the wheels touch down, but only if three very specific parameters are met. The flight/taxi switch has to be in flight. The power levers must be pulled back near flight idle, specifically less than flight idle plus 12 degrees, and the weight on reels proximity sensors must physically detect the landing. If all three of those align, the spoilers deploy automatically. But what happens if a malfunction actually jams this whole interconnected roll system? Well, pilots have to execute a very exact emergency sequence. If you picture the forward center console in the cockpit, normally the roll disc handle is spring-loaded in. This is our in-to-win together state, meaning both pilots share roll control over the ailerons and spoilers. But in a jam, a pilot has to grab that handle, pull it out to its absolute limit, and turn it 90 degrees clockwise or counterclockwise. Remember, pull and turn to unjam. This disengages the clutch and splits the controls. The pilot with the unjammed column gets the spoilers, and the other pilot gets the ailerons. This brilliantly illustrates exactly what happens mechanically for each pilot right after that disconnect clutch splits the controls. If the left column is free, that pilot is flying only with spoilers. That means the roll control forces are going to feel incredibly light, and they absolutely must avoid over-controlling. On the flip side, if the right column is free, the co-pilot flies the ailerons, but they have to closely monitor the spoiler 1 and 2 switch lights. All right, Section 3, pitch controls and elevators. So the Q400 uses a triple redundant hydraulic layout, basically ensuring the elevators always have power, even in severe system failure scenarios. Each elevator has 3 PCUs. The outboard PCUs run on hydraulic system 1, the center ones run on system 2, and the inboard PCUs sit patiently as a standby. They're powered by system 3, totally ready to take over if the main systems fail. Now, pitch trim is heavily automated, or it's inputted by the pilots via thumb switches. But if there are multiple conflicting pitch trim signals, the system strictly enforces a specific hierarchy. Pilot trim switches trump everything. They're number 1. Co-pilot commands come in second, and the autopilot, that's at the very bottom of the priority list. Let's move off the primary axes for Section 4, secondary controls, the flaps. What's actually really interesting here is the specific safety timing built right into the mechanical gate of the flaps selector lever. If you picture the power quadrant, to move the flaps, you can't just push the lever. You must pull up the trigger located just below the knob first. Think of it as trigger to travel. You gotta pull the trigger before the lever can move. Once you move the lever to your newly selected gate, say 0, 5, 10, 15, or 35 degrees, you have exactly 10 seconds to release that trigger, 10 seconds to set. If you don't release it within those 10 seconds, the flap simply won't move. Let's transition to Section 5, Q400 Gust Lock Systems. These are the ground safety mechanisms that protect those massive aerodynamic surfaces from violent wind damage when parked. And there's a really great contrast in how the aircraft achieves this. The ailerons use a physical, mechanical system that locks the surfaces in neutral via a trigger-released control lock lever right there in the cockpit. The rudder and elevators, however, they don't use physical pins or levers. They passively rely on trapped hydraulic fluid pressure within their actuators to create a stiff, immovable surface that fights off external forces. And finally, Section 6, the stall protection system. Because this system will literally push the control columns right out of the pilot's hands during a stall, it requires a highly structured daily pre-flight test. First, over on the pilot side console, you hold the stall-worn toggle switch in the Test 1 position for more than 10 seconds. 10 for Test 1 lets you test the first channel and literally feel the stick shaker activate, lighting up the number 1 fail and push or fail caution lights. Next, just let the spring-loaded switch return to the center off position to extinguish the lights and end the test. Center to settle. Finally, push it down to Test 2. 2 for 2 tests the second channel and lights up the number 2 fail caution light instead. Now, while in flight, you've got to constantly monitor these specific caution lights. If stall syst fail 1 or 2 or pusher syst fail illuminates, it means the critical stick shaker or pusher operation is compromised. The system is essentially telling the pilot that the automated safety net is no longer fully functional, which can happen if it's manually inhibited or fails self-monitoring. Which brings us to a pretty fascinating conclusion. The system allows pilots to physically override the automated stick pusher, but doing so requires applying up to 80 pounds of opposing force to break the clutch. As these intricate manual and automated systems work seamlessly to guarantee flight safety, what happens when human instinct clashes with a massive hydraulic override? It's a classic question of trusting calculated automation versus pilot intuition. Thank you so much for joining me on this explainer, and I hope this deep dive into the Bombardier Q400 leaves you eager to explore even more about the human factors in aviation.